So today, I want to talk a little bit more. Well, so, okay, so here's the plan for the rest of the week. This is the week plan. So today, I want to talk about more of 13.3, which covers arc length and curvature. I won't cover it all because I want to go slow enough to give this a full development. Tomorrow, we'll finish up 13.3, whatever's left over. I may not have the ability to go on to 13.4, and even if I do, it will be optional. So probably I just will finish up 13.3 on Thursday. We'll talk about a exam review. So I will post a final review sometime on Wednesday. On Thursday, you'll have a chance to talk about it. And then on Friday, especially since this class is got your final on Monday, right? We have a final like Monday afternoon. So my plan is to give Thursday and Friday both over to problem solving. So like if people have questions about stuff, you guys can come and ask. You're not required to be here, but I would strongly encourage you to be because this is a place to get your questions answered about what's going on. So we'll cover new material. So the stuff from 13 will be there as well as everything from the past. Okay. So this is my sort of general plan about how this is going to go. One of these days will be me doing a lot of talking and one will be you answering questions. Yep.
Sorry, did you say the review is going to be posted on Wednesday?
What's that?
Did you say the review is going to be posted?
I'm going to post it on Tuesday. I mean, so the best way to get started on reviewing for this after we get through 13.3, the absolute best way to get started is to go back and do the exam review for exam 1 and the exam review for exam 2 again. Okay. And if you need more questions in those categories, that's what sort of, I'll give alternative questions in that same category, right? Or places in the book to look at. Because there's really only 3 sections left, and really 2 sections that are going to be on the final that have been covered so far. Okay. Nothing? No. Gotcha. Is that you? I got it right, right? Cool. All right. So, with that said, I would like to go on to talking about 13.3. So yeah, as much, again, individual questions, particular areas that you're concerned about, you can ask me about. I am going to have an extended sort of, especially for this class, I think with the Monday office hours, I'm going to try to give at least 3 additional office hours this week, plus probably one on Monday morning before the exam. I know a lot of people won't be able to make that because they have Monday exams, but there's basically nothing else I can do. I mean, I can't move the exam. I'm sorry that you guys got pinched up against the top of the week. It's tough for a math class. Right, so let me pull up the book, which I have to do here because I forgot it. And we'll start about curvature. Just open. All right. Got a whole set of notes too. I forgot all that too. All right, so here's what we were talking about last time. So this is 13.3. This is new material. We're going to be with a brief review before we move on to new stuff. So the point of 13.3 in the beginning was the idea that if you had some function r of t, which was given by f of t, some vector function, and that function was differentiable, or otherwise none of this makes any sense at all, then the length of the curve, between r of a and r of b is L integral from a to b of the square root of x squared y dt squared squared, which we noticed last time was the same as the magnitude of this vector. So we wrote this as the integral from a to b of the length of the vector r prime of t. It says fail me on the vector. Okay. So we also defined a notion not just of arc length. The picture that you should have in mind here is you've got some curve C. This is R of A. This is R of B. And what this is measuring is the length of the curve between R of A and R of B. Okay. So we also defined something called the arc length function. So as for imagine that R of t is Ft T, and we have a domain between A and B, I can define the arc length function So what I'm going to do is, instead of thinking about the curve as having only a beginning and an end, I want to be able to figure out the length for any point in between the beginning and the end as well. The idea here is, if I had an R of A, curve went along, and I have an R B, I want to be able to say how long the curve is for any length in between. I want to be able to say how long this piece of the curve is. So that's called an S of t. Standard notation for this is S of t. And it's going to be the integral from A to t. And we have to, because we're using t as the variable here, we have to use a dummy variable in the integral. Use u, it doesn't matter, because what will happen is when we're done, we'll integrate this and then plug in the t. So what this function represents is the length from R of A to R of t. And it's a function of t because I can pick any t value I want between A and B. It's an arc-like function. That's an example of an arc-length function. Consider R of t equal to 2 cosine t, 2 sine t. Then S of t, I mean, I guess I got to give you a domain here. How about t falls between 0 and 2 pi? And S of t is going to be the integral from 0 to t of the length of R prime of t, R prime of u du. And let's compute the length of this vector. So R prime of t is the vector, I'll just take these derivatives, and I'm going to get minus 2 sine t. And the derivative of 2 sine t is 2 cosine t. And the length of that vector is the square root of minus 2 sine t squared plus 2 cosine t squared, which, if you did the exam, you notice this is basically identical to the problem on the exam, right? The idea here is that the sine squared and the cosine squared turn into a 1. This is the square root of 4. Negative 2 squared is positive 4. See, that's 1, so this is just 2. So the derivative of R prime of t is 2. So this is the integral from 0 to t of 2 du, which is 2u evaluated from 0 to t, which is 2. So that function is S of t. This is the arc length function. The interpretation of this is that you're on some circle. You start here at t is equal to 0, and then what you're saying is, okay, if you go along, let's say you're at the 0 point right here, when you go along out here to the point r of t, what we're measuring is this arc right here. And the length of this arc, s of t, is equal to 2t. Measures how far, like in distance, you went around the side of the circle. Does that make sense? And this is review of what we did last time. It was like a week ago, so I'm going to remind everybody. Yep.
I think you did answer this last time, but where is it?
So the u is only here because I need to integrate this function, but I'm already using t as the variable out here, so I can't have a t inside as well. So all I'm doing is saying it doesn't actually matter how I integrate this. At the end, I'm going to plug the t in. So I just picked some other variable name. So I'd say do the integration, and then at the end, plug in the limits. Okay. So what we want to do is we want to try to think about that the point of what we're going to do now is we're going to start thinking about how quickly a curve changes directions. Something that matters in a lot of contexts is how fast a curve changes directions, how fast it bends, how twisty it is. And one notion of trying to understand how twisty it is called curvature. So curvature comes from the following idea. So remember that t of t, which was the unit tangent vector, t of t is the unit tangent vector, and it was equal to r prime of t divided by the length of r prime of t. It's like we looked at what the derivative vector was doing, and then we divided by the length, so its only direction is all we're keeping track of. So you can imagine if you've got some curve C, and you computed t of t, the unit tangent vector, at any given point on the curve, what the tangent vector is telling you is just what direction the curve is moving at that point. Now let's suppose that this curve twists around really fast all of a sudden. Here, 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 here. So you'll notice that when the curve is bending really quickly, the unit tangent vector changes directions really fast, right? As the curve slides through this, I mean, when I look at this, I think, here it's changing directions very quickly. Here it's not changing directions very quickly. And then it kind of gradually changes directions, but it's changing directions really fast over here. And the idea is to keep track of how quickly the unit tangent vector is turning. The faster that t of t turns, the faster that this thing turns, the more the underlying curve is twisting, it's changing direction. So the idea, the big idea, C changes directions, or C is here, probably a word in English, twistier, it is actually, C is twistier if T of T changes directions quickly. That's kind of the idea that we're going for here. Is if I can keep track of what T of T is doing, how fast it's changing, if I can keep track of how fast T of T is changing, I'm in some way measuring how fast the curve is changing. Okay, so before we get into the technical aspects of this, we're going to do sort of an intuitive idea here, which is which circle is twistier? Why is the small one twistier?
Directions.
Yeah, the same. Yeah, so imagine like just in terms of arc length, right? And here's the idea. The curve is all we care about. We don't care about how fast this particle that makes this move is happening. We just care about the path that it makes, right? So if I look at one unit of distance change here, T of T might go from pointing like this to pointing like this, if this was one unit of length. The idea is that unit of length turns out to be the natural thing for chopping the curve up, right? Not how fast the particle that made the curve travel, but actually how far we traveled on the curve. Here, 1 unit of length might get you from this point all the way over here. So that seems like a pretty radical change for 1 unit of distance as compared to this one, right? In 1 unit of distance, t doesn't change much. Here, in 1 unit of distance, t changes a lot versus itself, right? So what this suggests is that the natural variable to consider in all these questions is not t, but s, the arc length variable. Because arc length is going to give us comparable ideas here. 1 unit of length here means this much change in t. 1 unit of length here means this. It doesn't matter how fast the particle is traveling. It only matters the path that it's on. Okay. So what we're going to do is we're going to define curvature in terms of units of length. So arc length is going to be the variable. So I have 2 things to say before we get into the actual definition. The first is, I actually know an expression for the derivative of, the idea here is that if I have s is equal to some function of t, arc length is a function of time. I don't want time to be the variable, so I want to reverse this somehow and write t as a function of s. This is hardly ever possible. But it's going to lead us to the formulas that we want. So what I mean here is almost every function we've been given, has looked like this. R of t is equal to 2 cosine t, 2 sine t. But this measures how quickly the particle is moving. It doesn't measure the path, and it doesn't tell us anything about arc length. So what I really want to do is to say, well, instead of considering t as the variable, when I'm studying curvature, I want s to be the variable. S tells us how far we've moved along the path. So I'd like to be able, oh man, sure would be nice if I could say, well, if we could do this, if we could say, oh, if only I could write t, the time, in terms of how far along the curve we are. So you figure out how far along the curve you are, you figure out the time that came from, and then you put that up into the function. So this sort of thing, R of t of s, this is what's called parametrization by arc length. I know it's ridiculous because, we haven't done anything like this. It's very abstract. But there's a really, really awesome way to work with this that doesn't ever require us to actually solve this equation. I don't have to find t as a function of s by solving some equation. I guess I can do this. I can use engineer tricks, basically. First trick. Trick 1. If I had s of t is equal to the integral from a to b of r prime of u du, and I took the t derivative of both sides, the left-hand side, I'm going to take that one for myself. That's ds dt. What's the right-hand side? Derivative of the integral. What's that? Why is that? This has a name, though, when you take a derivative of the integral. If you think way back. This is a fundamental theorem of calculus, part 1. So the fundamental theorem of calculus part 1 says if you take a derivative of an integral, you throw the integrals away, right? Differentiating and integrating are opposite. Okay, so we're going to use this fact. We're going to store that fact. Okay, so thinking of s as the variable. That is, I want to compare like distance traveled along a path, not how quickly I did it. Distance traveled. I define, oh man, I gotta draw kappa. Kappa, which is the curvature, be equal to the length of TDS. So this is the definition of curvature. In the picture that we drew before, what you should be thinking here is curvature is going to be bigger when this derivative moves faster in terms of arc length. So on this curve, 1 unit of arc length gets you a change in derivative that's pretty small, right? If you think about this as sort of like delta S, a little bit of unit change in the S in the arc length, you get this change in T of S. Whereas if you're on a little tiny circle, the same unit arc length, this is also delta S, for the same change in arc length, you have a vector that pointed this way and now it's pointing like this. Okay, this is why we're thinking of S as the variable. This vector changed a lot for 1 unit arc length. This vector didn't change very much. So this is why we use this to measure curvature. The magnitude of the derivative is really measuring how much that tangent vector has changed direction. How much unit tangent has changed per unit arc length. Because I need these curves to be comparable. And the path is what I'm interested in, not the particle that's making the path. Okay, so here's trick 2. This formula is impossible to compute with, so we never do. But it's going to give us all the rest of the formulas. So the very first thing we do is we write down the first computational formula, which looks like this. Noticing the following. dt. Here's the engineer's trick. Trick 2. If I could, now we've already calculated this guy, right? T is a function of T. I can take its T derivative. This is easy. We know how to do this. dt, that's the thing we can do. So now we're going to uncancel a ds into this thing because we're engineers or applied mathematicians. We say, well, obviously that's equal to dt ds times ds dt. Because after all, ds and ds cancel each other, right? But I know what this is by trick 1. Trick 1 says that d by dt is equal to d by dt ds times the length of r prime. So this move right here, that was trick 1. And if you rearrange this, you'll notice that dt ds is equal to dt dt divided by the length of r prime t. So if you divide both sides by this quantity, you get this. That's just algebra. And that means that the first computational formula for the curvature, well, curvature is the magnitude of dt ds, but look, S is basically completely vanished. I can do this entirely in terms of T. So that gets us another expression for curvature. That's a terrible kappa. Another description of curvature is the length of dt ds is the same as the length of t prime of t divided by the length. This formula gets used all the time. So that's the first sort of computational formula for curvature. So with that, actually, we can we can compute the curvature of a circle. So let's compute curvature of RT is equal to A cosine T, B sine T. Now notice, I don't care about S anymore, right? The S was a tool that got us to this computational formula. So I'm going to try to, that's not a circle if I put an A and B, so A and A. So I want to compute K is equal to the length of T prime of T divided by the length of R prime of T. Okay. So if we do that, I'll just erase my page that I was at. R prime of T, actually, let's actually, R of T was A cosine T, A sine T. R prime of T, this is the same as the computation we just did, minus A sine T times A cosine T in the second slot. The length of R prime is going to be the square root of minus A sine T squared plus A cosine T squared. And hopefully you guys will believe me if I tell you this turns out to be A. Cosine squared and sine squared turn into a 1. There's an A squared running around on the inside that factors out as an A. Okay? So that's the length of R prime of T. So what's T of T? T of T is supposed to be R prime of T divided by the length of R prime of T, which is equal to, well, I know R prime, it's right here, minus A sine T, A cosine T, that's R prime, divided by the length of R prime, well, the length of R prime is A. And so we get T of T is equal to, okay, so the A goes in here and turns that A into a 1. So we get minus sine T cosine T. If you've done this correctly, this is a unit vector. Is that a unit vector? Is cosine squared plus sine squared equal to 1? Then that's a unit vector. It's on the unit circle. That has to be. I don't know if you guys can tell that curvature computations oftentimes are very, very lengthy. So that's T of T, but we're not done because curvature is the length of T prime divided by the length of R prime. Well, I've already got length of R prime, but that's done. I need to compute the length of the derivative of that is minus the sine of T cosine T. So T prime of T is minus the cosine of T times minus the sine of T. The length of T prime of T, square root of minus cosine T squared plus minus sine T squared, which is 1. That's not always the case, by the way. This has to do with the fact that it's a circle. So what that means is curvature, which is the length of T prime of T divided by the length of R prime of T, is equal to 1 over A. So now let's see if we can think about, after I let you guys catch up with this, let's see if we can interpret what exactly this means. So when you're looking at an equation like this, what the A represents is the radius of the circle. So what this says is a circle, what would the curvature be for a circle with radius 10? If A is equal to 10, that's the radius. What's the curvature? 1/10. If A is equal to 1/2, what's the curvature? 1 over 1/2, which is 2. Small radius means large curvature. Large radius means small curvature. Essentially what we're saying is if you have a circle that has a very gentle curve because the radius is large, for a fixed unit length, the derivative here doesn't change very quickly at all. But on a circle that looks like this, the radius changes the tangent changes very quickly relative to arc length. Okay, this is sort of like the A equals 10 case, and this is the A is equal to 1/2 case. Here the curvature is very small. Here the curvature is very high. Okay, so this is a natural way. This sort of computation is a natural way of capturing how quickly these things go. Okay, this idea is really important. And then basically once you have the idea of curvature, what that means is curvature calculated for not a circle, but for a generic curve. I'm not going to give you any more formulas today. I just want to give you a picture. Imagine you had a curve that changed like this. The way you should think about what curvature is doing in the background, what you're measuring, is you're not finding tangent lines to the curve. What you're actually doing is at a given point at the curve, if you want to measure how curved that is at that point, you find the size of the circle that matches the curve there. So it's like you're finding tangent circles instead of tangent lines. These have a fancy Latin name called an osculating circle. It actually means kissing, right? So it's a circle that's cotangent with the curve. And if you draw a little tiny circle where like to approximate a curve, that means that's a high curvature spot. Small circle, high curvature. Whereas over here, if you try to draw a circle that approximated the curve over here, you'd have to draw a circle that looks like this. It's a terrible circle, but hopefully you get the point here, right? Which is that the circle that matches the curve at that point has a huge radius by comparison. So a big circle to match the curvature of the curve, large circle means low curvature. So this idea of curvature corresponds with our intuition about how quickly the curve is changing directions. The size of the circle that approximates the curve tells you how quickly the curve is changing, or how fast it's wrapping around the circle at that point. All right. So basically, the upshot of curvature is, so here's what we got so far for curvature. The definition of curvature is the length of ECES. That's a theoretical tool, not a computational one. Then we wrote down a better version of this, which is the length. I mean, better in the sense that it's doable, but not worse in the sense you got to do even more derivatives. T prime of T over R prime of T. Now there's an even better one that does not involve having to do any of this stuff if you're willing to take a cross product. So this one is the length of R prime of T crossed with R prime prime of T divided by the length of R prime of T cubed. So I'll make you a promise. The curvature formulas, when I give you the final, I just give you the curvature formulas. There's three of them. There's three computational formulas for curvature. I will just write these down. Just like I did with the derivative stuff, I'll give you these. I want you to be able to use the curvature stuff. I don't really care if you carry it around your head. The idea where this formula actually comes from is if you take this equation and you sort of write it out and expand it, you can actually see that one piece of it looks like a cross product. It's like a bunch of nasty algebra, and it just happens to be the case that when you're done, this is what falls out. So this is derived in the book. I do not expect you to know the derivation. I do expect you to be able to compute with this if it's convenient. Oftentimes, this is a choice of convenience when you're choosing a formula to compute curvature, right? If you don't want to compute the unit tangent vector, or the unit tangent vector is just nasty, which sometimes it is, right? Because in a circle, the curvature was constant, 1 over A. That's not the case for a general curve. So maybe if you divide by some horrible square root with a bunch of stuff running around inside and you try to take its derivative, good luck. This does not actually require that you take derivatives of a unit tangent. That's the virtue of this one. Okay. All right, so next time, what we're going to look at is, we'll do an example of this. Next time, we'll do an example of this. I'll give you another computational formula for the curvature, and we'll move into talking about how we can use the ideas of vectors here to measure not just curvature, but torque or twisting of a curve in sort of the radial sense. There's one way the curves turn like this, that's sort of the curvature way. But if you were sitting on a roller coaster and you were moving along a path and things started to twist, you wouldn't just be going this way, you'd also be turning this way. And so we can pick that up with vectors too.
No torque.
I mean, we're not doing it in physics language. All right, so good job on your exams. If you got questions, I'd be happy to answer. I'll see you guys next time. Wait, hold on, let me kill this recording. So.